Hello and greetings, everyone. I am Professor L, and this is another live stream for Math Help. So if you need help with your math or you just want to hang out and do some math with me, you're more than welcome to put a problem in the chat. Um, in the meantime, I am trying to stay relevant, so I decided to talk about force vectors, and it's been a long time since I've uh, even thought about force vectors, but I do know a little bit about it, and I knew enough to know what to ask to look some stuff up. So I'm going to do my very best to try to present something on force vectors, and then yeah, so we'll just take it from there. And whatever I need to do to revise my methods, I'll work on it. The reason why I chose force vectors after this picture is because there's a technique using parallelograms to calculate the magnitude or the resultant force when you add vectors, and so it's pretty cool. So I thought maybe I would get into the vectors a little bit, and then it's kind of I don't know if I'll show the parallelogram method today. Maybe we will. Anyway, I just thought we'll work on vectors because it's kind of relevant because of this parallelogram. This was a geometry problem that we used a little trig to solve on Friday, and it was fun and it worked out. So try to keep things related and not go off on too many tangents. And it's just been really interesting so far watching all my videos and trying to improve. Everybody's got to start somewhere. So I thought we would start by, or I would start by just talking about what a vector is. It's not the character that stole the pyramids on the movie Despicable Me. That was a cute movie, but it's a vector is it's a, I guess you would call it a quantity in mathematics that is illustrated best by a array. So vectors, and what distinguishes a number from a vector is the fact that it has a direction. And we'll label this one force vectors. And, maybe in some other universe or some other time I'll be more practiced, and I probably should practice these and be real structured about these live sessions, but this is where I'm at right now, so we'll just go with it. All right, so when you're talking about a vector, so let's go ahead and just write. I'm going to start with the Cartesian coordinate system. I'm not even sure how to even start talking about this. But if we take the Cartesian coordinate system and we recall that if we had a radius of 1, or we have a value of 1 and we have a radius of 1, then that makes the unit circle. See if we can get these kind of, okay, -1, -1. All right, so you have the unit circle. It's centered at the origin with a radius of 1, and then what happens is if you draw a radius, or let's see, if you attempt to draw the radius out here, there's a point P on the circle at some point, and the coordinates of P of x comma y, and we draw this ray. It's a radius here, and it's a point P. That because of the fact that this is the x distance and this is the y distance, and then this would be r, what we have is a Pythagorean, because this is a right triangle. And so we have a Pythagorean. And so by the Pythagorean theorem, we have x squared plus y squared equals r squared. And so we'll just use Pythagorean. Theorem. Okay, and so that's kind of where it starts. And so then if you allow x to equal cosine, and it always takes in a theta or an angle, and y equals sine of theta, then what you have when you plug in here is you'll have cosine theta squared plus sine of theta squared, and that's going to equal r squared. And then, let's see, it's not represented like that. They like to represent the cosine in the notation because they like to square the cos and then tack on the theta. So that becomes cosine squared theta plus sine squared theta, and that still equals r squared. And so this is for r, which actually equals 1. But it'll work for any. So when r equals 1, we've got the Pythagorean. So you just plug in 1 here for r, and you end up with, and then you rearrange it in the Pythagorean identity, sine squared theta plus cosine squared theta equal 1 is the Pythagorean identity. But here's where it comes from. It comes from this unit circle. And what it's doing is you're taking an angle theta here. Okay. And the theta is always, it's a reference angle. So theta is always between 0 and 90 degrees for reference angles. So it's always an acute angle. So it's going to be acute. And then you would just figure out the actual, like if theta was wherever it was, it could be multiple revolutions around, and then it's stuck here in the first quadrant. And what you would do is the game, essentially of finding the angle is just finding the acute angle, the reference angle, and then just adding on or subtracting 360, because this is 0 here and then this is 360 here. So you go counterclockwise motion around that circle, and each time you pass this point, you're accumulating. So it's more than 360 or less than 360. And I did not get enough sleep last night, so I hope that I'm not being too loopy. But yeah, so basically, this is the Pythagorean identity. This is where it comes from, and it's also related to what we're doing with these force vectors, because whenever you let x equal cosine theta and y equals sine theta, what happens is the math checks out, and it's beautiful for the unit circle that x becomes like, if you want to find any point on this unit circle, you can plug in the angle, and it'll tell you the side lengths. And that's the x value. Notice it's horizontal, and the y value is a vertical. Okay, so this is the y-axis, and these are the vertical values along the y-axis. And then this is the this would be the x-axis, and all the values along this axis are going to be horizontal along this horizon. Anyway, so I hope that kind of makes sense. But this is the same idea about finding these force vectors, is and using the trig, and you use right triangles, and it's a very similar process. But what a vector is, vectors have, and I don't know if I want to erase. All right, so the only thing we need from here is this cosine theta and the y. So let me erase and draw another triangle and talk a little bit more about what a vector is. Vectors have two things that make it a vector. It's a magnitude and a direction. So we need another Cartesian coordinate system here, a clean one. And we're going to draw our vectors using like a compass, where this is north, and then the way it works is the positive direction is east, and then you have south and west, and most people understand the way a compass works. So if it's taken out of the north, you're going to have to drop your angle this direction. If it's taken from the east, you'll find your acute angle that direction. So it's a little skill in itself, and I'm remembering it too. I was much better at navigation problems when I was in the throes of my education in my math in college. This was like something I took for granted, and now I'm trying to relearn it, and it's like, oh, I'm starting to realize how much I have forgotten, and it is scary, but hopefully I'll remember. And all right, so when you're marking a vector, usually you'll have they'll have to tell you the direction, and then the magnitude is just the number. It's just the size of the number, separate. So it's the absolute value. So let's put a definition up here. Magnitude. Okay. The magnitude of V, your vector V, is said to be, and this is how you represent magnitude. Usually there's like something over the top, but and it's taken from the Pythagorean. So the magnitude is the diagonal. So it becomes the square root of let's see, it's x squared plus y squared. And so we have the magnitude, and then the direction is just the sign. So you'd have in some sort of degrees. So you have to have a magnitude and a direction. So we'll just say north, south, east, west. So you have to have a magnitude and a direction. All right, so let me just get an example out here, because I found this in this old trig book. And so if we were going to, and I'm not even going to work this problem yet, I just want to draw the vector. Here's some examples. So 17 pounds, 17.8, and it's north. So, for example, 17 pounds forced upwards. Okay, so you're taking 17 pounds and you're lifting it straight up. Then this is north. So so I'm going to represent that vector, and we'll just say we'll go up 17. And there's your vector. It's right on the y-axis. Okay, and its size is 17. Let's draw another one. Let's draw one that's not going to be right on the line. Let's draw one like here. This one says 50 pounds acting north, 21 degrees and 16 minutes east. So we'll have to get a compass. Do I have one handy in here? Okay, let me just guess. Okay, so 21 degrees will be, let's see, 45 is about half of 45. So I'm going to say it's probably like right in here. Well, and it's just a rough sketch. Okay. So we're going to say this angle, and we'll call it alpha. We'll say alpha. Okay. And it's north. And this is a bearing. This is an introduction. Brief, general, very rough introduction to bearing. So it's 21 degrees. And then it's, what did I say? How many minutes? 16 minutes east. So since we started with north, then we're going to make sure that we're coming from that direction. Okay. And this becomes my acute reference angle, so that this vector, the size of it was 50 pounds. So it was 50 pounds. Let me just see if I can write it all the way out. So we've got 50 pounds in north, 21 degrees, 16 minutes east. Okay, so I'm going to erase that and just put the alpha on there. 21:16. So here's your alpha. 21 degrees, 16 minutes. And if I wanted to change that to a decimal, I could do that. All you're doing, the way it works is there's 360 degrees. It's split up even further to 60 minutes, and then there's 60 seconds in a minute. So every 60 minutes, there's another degree. So you would just round. So whenever you get up to 60 here, this would become 22 degrees. And so on and so forth. So I guess the minutes would, so basically the degrees would, whenever you transfer it to time and you change it over using conversions, actually, that's a fun problem. Maybe I'll find it. But what you do is you convert and you superimpose a clock over the grid system, and then you convert time and it works out. So 16, there's 60 minutes in a degree, and there's 360 degrees in a circle. And so we got that from the Babylonians. They had the base 60 numeration system, and that's the reason why there are 60 minutes in an hour and 60 seconds in a minute. It's because they decided to split that all up. And probably the Gregorian calendar was probably mimicked off of that as well, because it was the circle of 360 degrees for a lot of similarities. All right, so back on force vectors. So this is a vector, basically V here. Okay. And basically where the trick comes in, okay, is what we're doing is we can use this to either add or whatever we're going to do. If you have two vectors, you can add them together. There's also a way to calculate the resultant vector when you add them together. So if you had like a vector here and you had another vector here, this is a little advanced for vectors, but I can probably go ahead and try to work this one. 150 pounds north, 49.28 west. So the other one I have is 158 pounds, and it's north 49 degrees, 28 minutes. Minutes west. Then if I was going to try to locate this vector here. So we've got these two vectors. This one's 158 pounds. So it has a magnitude of 158. And the direction it's heading is 49 degrees and 28 minutes west, north. So from the north, in the westerly direction now, we have this other vector. And I'm going to erase this one because it's not on there anymore. This is different. Let's see. It's 49, so I have to guess. So if I cut it right in half, that's about 45. And so I want to be a little bit more on this side of it, but it's just a rough sketch. So it's just enough to get us close. Oh, we'll go with it. It's fine. So we've got this other vector that's 158. Okay. And it's got this direction. Okay. And so this one. And we can call that one beta. And so we've got beta over here is going to equal at 49 degrees and 28 minutes. And so we'll just keep an eye on that one. All right. And so if your vectors are too large, there is a way to draw them out. So there's a tip to tail method of adding vectors, and there's also the parallelogram method. And then I think that because if you can imagine if they were drawn to scale, which I don't think they are, this one would have to be much shorter. It forms a parallelogram. And I might save that one for next time because I realize I'm already 26 minutes and I haven't even worked the problem yet. But if I want to go ahead and find them just algebraically, what you're going to do is you'll take your vector. So like just take this one and we'll say over here, I think it's about that direction. What we're doing is we're using the x-axis and we're splitting it up into vertical and horizontal components. And so we have the angle alpha, and this vertical component here is going to become it's the magnitude or of the so it has, and then this is going to be the y, so this is going to become I erased it. This is y equals sine theta, and then this one is x equals cosine theta. So we have these components here. The and this is called the vertical. And then this one is going to be called the horizontal. Okay. And in order to add these vectors algebraically, you've got to split them up into the components and then add them physically. Then you add their components. So like I'm going to split both of them up using this fact, y is sine theta and x is cosine theta, and this fact that the force, it's kind of like F equals ma, but for vectors, it's just the force is going to equal its the magnitude of the vector. So how do I write that? So it's the force is the gravity times, so we'll say F sub x is cosine theta, and F sub y is going to be F sine theta, where F is the magnitude. And again, this is me trying to very loosely and professionally present this for the first time, and I know I shouldn't be doing on live television, but we're just going with it. All right, I should probably practice this 100 times before I go live, but I haven't really practiced it at all. I just kind of looked up some things. So, all right, since we have these formulas, then we can quickly use, and in this case, it's not theta, we're going to change it to alpha, whatever our angle is. So theta is kind of a generic general term, and so since I'm using alpha here, stay consistent with my variables. There you go. Okay. All right, so now what we can do is we're just going to take the values. So we'll call this vector the first one, and this one the second one. And you have the magnitude of your vector is 50, and you have your angle. So this is your M, and this is your angle. And so what you're going to do is just by these definitions, the force, the F components of, we'll say that first vector, try to stay organized. For the first vector, the F component is going to be 50 cosine of 21 degrees and 16 minutes. And we'll plug that in the calculator in just a minute. the y component here is going to be for your first vector is going to be 50, not x, y, 50 sine 21 degrees and 16 minutes. Okay. And we'll leave a room there and we'll mark them. We'll work those. All right, let's go ahead and plug those in a calculator. So 50 cosine 21 degrees, 16 minutes. The calculator does have an angle button on here. It's the second feature. If you have one of these fancy calculators, it will give you the exact figure, minutes. So I'm just going to round out. So this is 46.59512005, and that is an approximation. And we'll do sine now. And sine is 18.1354665. All right, so we got the first one, and now we have to calculate the second one. Let's get this over. All right, so we'll put it here. So vector, block that off. Vector 2. Okay, and the force of the x component is going to equal, and that was 158 pounds. So the force is 158. So we're going to say cosine of 49 degrees and 28 minutes. And then we'll leave a line and go ahead and calculate F force of y. It's the y component. So we can add these vectors. And this is going to be 158. It's the magnitude times the sine of your angle, 49 degrees and 28 minutes. All right, and let's plug these in. 8 sine 49 degrees 28 minutes. And I calculated sine first, it's fine. It's 120.0844245. And it's kind of similar to the dot product, but what you're doing is you're going to add these vectors. All right, so let's figure out x. And all I'm doing is replacing the cosine. That's 102.6826.713. All right, so what it boils down to is up here, we'll do it off to the side here. And so we've got vector 1 plus vector 2. And the way that works is you have to add your x components. So we've got f sub 1. So this is f of x sub 1 plus f of x sub 2 and f of y sub 1 plus f of y sub 2. Basically, so you have two different components. You have an x and a y, and you have to add them together. And so, and this is to calculate magnitude. So f of x sub 1 plus f of x sub 2 equals, let's round it to 10th place. 46.6. What's this value right here? Plus this value, 102.7. Uh, 149.3. So this is the force of the x component. F of the x. And we'll box that. And then we've got to calculate the forces of y. So f of, I've got to get out of the way somehow. Maybe I can do it this way. F of sub y sub 1 plus f force of the y components here. That's going to be, let's say 18.1 plus 120.1. And so that's kind of easy for me to calculate. It's what was that, 140.2. All right, I got 138.2. And so this is the forces sub y. All right. And so did I put the magnitude up here? I did. So we're going to use this formula to calculate the magnitude. And this is how you do it if you don't have measurements. So the other ways of calculating the magnitude involve measurement. You have to have an exact figure. Like when I drew these to scale, you would have to have an actual the right angle, and it has to be more exact if you're going to use those other methods. But this one will work. It's the algebra. All right, so finally, the magnitude of B is going to be that formula. Take it from the Pythagorean, and the x values squared plus the y values squared. So f of x was 149. You got 149.3 y squared plus 138.2 quantity squared. I need to start recording these videos first thing in the morning because that's when I do the best math. And then I just post them, or just pick a better time for the live schedule because evening is not a good time to do math. It's just And it's tough. Much better in the morning, but sometimes we can't always pick the ideal time to do the math in our society, unfortunately. Okay, I'm just plugging this in to calculate it. So, right, 149.3 squared plus 138.2 quantity squared, and that was a square root, and I'm getting 203.444, and again, this is an approximation, so I'll be careful with that. 444.6608. And this is how you would calculate the magnitude of that vector algebraically. And I guess I could probably check to see if it's correct. Which number was that one? And no, I can't, because it is a even problem and they only have the odd problems in the back. But that's okay. If it's not the correct answer, then it was because of a minor arithmetic error. Those do pop up sometimes, and unfortunately, I'm not impervious to those. But more importantly, that's the method of doing it. I know that was kind of a crash course in finding the magnitude. What the magnitude actually is it's the resultant of adding those. So this is the magnitude of the resultant. Because what we did was we took these two vectors and we added them together, and that resultant vector most likely would be here somewhere. But what we'd have to do again is we would use the tip to tail method to determine that, and that requires the actual measurement. So your vector would actually have to be like this one said 50, it would have to be like the quantity 50 somehow. And this one was 158. Oh, this one was 50, 158. Still, you'd have to actually have the quantities to be more exact in order to use those methods. Anyway, all right. I think that I am going to go ahead and stop there. I realized that it was kind of iffy, and I almost didn't even have a live stream tonight because of the fact that I was so tired. I was like, I don't know. I don't know how it's going to turn out. It's not a good combination. You got to be rested when you're doing that. Unless you're just informally hanging out on your board and being yeah. I was going to say goofy goober, but I went ahead and said it. All right. Well, anyways, with all of that being said, I am going to go ahead and end my stream. And yeah. All right. Thank you so much for watching my videos. If you watched this, and yeah, I will see you again tomorrow. I will be back again, and I will again try to do my very best to stay relevant and to present something useful in the math related. Anyway, again, thank you. I hope you have a wonderful rest of your evening, and I will see you next time. Bye.